Good afternoon, everybody. Today, we're going to talk about problem number 2, sleeping in class, of the USACO 2022 February contest Platinum level. The question is quite interesting. Basically, is you have a series of numbers, right? Each of them is in the up to 1 to the power of 18. And you basically want to take this and regroup it into a set of fixed numbers, for example, number qi. Okay, so when you regroup, you can take any of the two adjacent numbers, you can merge them together, or you can take any number, you can split together. Right. So if you take this case, right? So for example, you have 1, 2, 3, 1, 1, 6. Okay, so you have 1, 2, 3, 1, 1. Sorry, 1, 1, 4. And then let's say your target number is 3. Okay. Target equals 3. So first thing you can do is you can merge those two numbers together, right? It becomes 3, 3. And then you can merge those three numbers together. I mean, the second step, you merge 6. The third step, you split 6 into 3, right? So that's your first step, second step, third step. I mean, this take 2 steps. 1 plus 1 take 2 steps. Step 2 and step 3, and this is step 4. So a total of 4 steps. So how do we think about this problem? The way to think about it is to use a concept called worst to best approach. Okay. It is in this code force block. It says worst to best option approach. The way to think about this is I want to merge all of the, I want to split this all to a single number, right? Let's say single number q. Okay. So if this is sum, okay, let's say the sum of this is, let's call it s. Okay. So each of this is a q, right? So obviously, if q is not if s is not divisible by q, then you cannot do it, right? So that means answer is -1. Okay. So let's only, okay, so that's what we know. So let's only think about the case that q is divisible by s. Okay, that's the only thing we're going to think about. Then I have a stupid way to do this. So let's say 1, 2, 3, 1, 1, 4, right? The first step, step 1, I will merge all of this into one big number, into one big number s, right? So merge this into this, take the sum, merge into this, take the sum, merge into this, take the sum, merge into this, take sum, merge into this, right? So merge into one single number s. So obviously that take a -1 step, right? So then my step number 2 is, now I have my answer, now I have one single number s, right? So then I can take the s, split into q's, each of the q. So obviously that take s divided by q -1 step, right? So I mean moves, as they call it moves, right? How many so how many perform how many moves, right? it takes this much moves. Okay, so that's my stupid way, right? So, but I can do it. So I have a way of doing it. But if you look at the example I just had here, right? So how do I optimize this? You know, when I merge 1 to 2 into 3, then what I said is I take this 3 and merge this 2 into 3 becomes 6. But however, I already have a 3. You know, let's say my Q is 3, right? I already have a 3. Then I don't need to split. I don't need to merge it, right? Because I can leave this. Then I can just start from here. Okay. Obviously, when I go from here to here, is I merge it together, right? So that is my pre-sum. Okay. So let's call it pre-sum. You know, pre-sum of I, right, is sigma from K from 1 to I, right? Basically of this A of K, right? So if my pre-sum of I is divisible by, if divisible by Q, I did it better. If my pre-sum of I is divisible by Q, then I no need to merge, right? So that's way, you know, this is my optimization. So how many I have it? Let's say if I have, let's call it, you know, let's say I have P of those. Let's call it PD, P of this derivable. Let's say if I have all those pre-sum calculated, the number of pre-sum that is divisible by Q, let's say it's a PD of them, right? So then each time I have this, I don't have to do this combine them together and split, right? So every of this, I saved 2 actions, right? I don't need to do step 1, I don't need to do step 2. So I have 2, each of them, I saved 2 actions. But obviously you don't need to do the last one, just like you have n of them, you merge them together, you only need n minus 1, right? So that's the how many I can save, I can save. So basically the total is n minus 1 plus s divided by q minus 1, the minus, that's the thing I don't need to do, number of p's that is divisible by d minus 1. So that is m plus s divided by q minus 2 times number of pt. Right? That's my answer. Okay. In the condition s is divisible by q. Right? So n is obviously the original number, right? So that's O of 1. S divided by q, that's just a division, that's Q of 1. So number of PDs, so number of pre-sum, that is divisible by Q, right? This I can easily do it in O(n) of O(n) squared, right? So I do for loop, you know, for each one of them, I calculate how many they have, right? So pre-sum, of course, you calculate once. For each Q, you loop through the pre-sum, and then you have what is called, this time you have 7 of them, right? You have Q of them. Okay, so you can do it O, Q, N, right? So N squared. That's obviously it's too slow. Now the question is basically, how do I calculate this faster? That is basically the question. Okay. Then when we're doing things like this, always we can always do it by take this into a break into its prime factors, right? So let's first do this. Okay, I have a pre-sum, right? I want to make, let's call this new. Okay, if I define a new pre-sum, okay, which is GCD of this pre-sum of I and the total of S, right? If since my S is divisible by Q, right? So if I want number of pre-sum that is divisible by Q, right? That's basic. If we already know this is divisible by Q, so that's the same as saying this new pre-sum is also divisible by Q, right? So we only need to look at this. The reason I want to do this is I want to make this number less than S. Okay, so my question is number of new pre-sum, which is a GCD of pre-sum at S, that is divisible by S. The reason I do this is then if I want to make this less than S, then I can just factor this out. Okay, so for let's S, I can written into bunch of prime number, right? So for example, prime number 1 of factor power of K1, prime number of 2 of factor of K2. We know how to do this, right? We can how to do this. Okay, then this Q, Q is the new pre-sum is divisible by S, right? So divisible by Q. So new pre-sum has to be some factor of this, right? So new pre-sum has to can be written by, let's say P1 have prime factor of K1 prime, P2 has prime factor of K2 prime, and so on and so forth. Okay. Like many problems, if I can pre-calculate, right? So this new pre-sum is less. New pre-sum is already said, right? Has to be less equal to S, right? So if I can pre-calculate all the possible combinations, using this prime factor, then I can, in O n log n time, then I can easily get out of calculate. Then for each query, it's just O1, right? So basically, it's like if I can do a DP, the first is what's the power for prime number K1 for prime number P1, right? So what's the power for prime number P2? What's the factor for prime number P3, and so on and so forth, right? If I can do this DP, then when I look at, each Q, I can just easily, right? I can easily calculate how many new pre-sum, so this is number of new pre-sum that is divisible by Q, right? So this new pre-sum can be written in that format. Okay, so how do I do the problem? Obviously, now you think I made the problem worse, right? I made the problem n to the power of, whatever, how many prime number you have, let's say of x prime numbers. You think I made it that difficult? For example, if you have 2 prime numbers, our standard way approach it is, as you have dp of ij, right? If you have this, standard way of doing this is you do this, and this way you can undo, right? So if I have lambda prime numbers, I think I made it much worse. But actually, there's a way to do this multi-dimensional thing faster. It is called sum over subset approach. Okay, so again, this is in the Benjamin Chee's USACO guide class. Okay, as I said, if you want to solve current Platon level problems, you really need to study the advanced level. So what does sum over subset do? It basically takes this and you can calculate it by n log n. The way it does is, if you think about your number is represented by, let's say by certain masks, right? In my case, right, it's represented by certain marks. You can split, basically you can split, think about split it into a tree by turning some bits on, some bits off, right? So you can continue split over into a tree. Then you don't have to calculate, you don't have to loop through this. You can loop through tree and then you merge, right? You go to the bottom, you merge up. And we know tree is n log n, right? So that's basically the concept. Of course, you have to go through the details and to understand how the sum over subset works. Okay, and read that problem and read read the code force instructions. Also read the gigs for gig instructions. Okay, so that will give you an idea how that works. We haven't had this kind of problem in USACO yet, but we have seen that in code force a couple of times, and there's a Japan ROI problem like that. So study this. This is basically turn that multi-dimensional dp into O n log n. Okay, so now you're asking me, how big this thing will be? S, right? So it was set over here. S is less than the sum of all this, right? Is less than 10 to n. So S is less equal 10 to the power of 18. There's a concept. There's a concept called, if I remember the term correctly, highly composite numbers. So if you look at the math word, okay, it's highly composite number is basically for all the numbers less than, let's say, 10 to the power of 18, what is, if you break into the prime factors and you make all the possible combinations out of those primes, and how many numbers you can make, okay? So sigma 0, okay? So, as I was saying, right? So how many combinations, possible combinations you can make? So read this highly composite numbers, and then you find out for S less equal to 10 to the power 18, the maximum composite composition you can make is 10, 103, 680. that many factors, factorial sectors you can make, right? So that is, so now you know the maximum is, I mean, this n is not the original n I was talking about, this, yeah, that number. So that is 10 to the power of 5, right? So you have sigma that of log 10 to the power of 5. Okay. So that's the complexity you will have. So that's now. By the way, from this is when we set the DP, right? We said in order to make a DP work, you need to do two things. Once you need to be able to define the state, which we clearly define. Second is you need to be able to describe the transition from one state to another state, which is very obvious, very easy to do, right? Once we describe it this way. Okay, so I will not go into that details. The key is really how to not do it in n to the power of x complexity, but do it in n log n complexity by using sum over subset approach. Okay, so then what's the last thing left to do is I need to make all the factorial, right? So how to calculate the prime factorial? It is for s less equal 10 to the power 18. If we use a standard approach, and this is to solve this problem. So what you need to do is, if you just Google fastest prime factor algorithm, okay? So the one I usually use is, if you go to a Stack Overflow, remember, right? The place we're always looking for hint is Stack Overflow, Code Force, and obviously Benjamin Chi's USACO guide. That's something you have to do. You have to learn. So fastest factorial algorithms. I like to use this one, Pollard real algorithms. That's a description of this algorithm. Okay, so it has or if you look at there's actually implementation of this on Geeks for Geeks. How to implement this, and obviously not a brute force approach, right? Yeah. So there's an explanation of how this thing works, and there's a sample code of how to do this. Okay, so I'll take that as a homework for you to go back to look at it. So that is Pollard's real algorithm for faster prime factorial. Okay, so that will get you into the time limit. Okay, so let's go back, look at what we did. So first is we figure out a approach is we merge everything into one number, sum of s, and then we split it back here. That's a stupid way of doing it, but we'll reach the result. The next step is, how do I optimize it? I can optimize it when I merge those from left and right together. As soon as this pre-sum is divisible by Q, I don't have to merge them anymore because I know they already give you the good result, right? So I can save this much. So basically, I can save number of pre-sum that is divisible by Q. That's how much I can save, 2 times, right? Because what I saved is 1 time merge, 1 time split. Let me write it down. So this is merge. This is split. So the problem left is we need to calculate how many of the pre-sum is divisible by Q, and we need to optimize it from n squared to n log n. And the way we did it is to look at the prime factors of S and use that to describe the state. And the transition is easy, but this calculation are going to, if you just brute force do it, it's going to take very long. The way to optimize it, this is to use the sum over set of subset DP approach, which you should study from Benjamin Q's USACO guide. Basically, you convert that into a tree. And we all know tree is n log n. I mean, this n is not the number of n there, okay? And by using the highly composite number estimation, we know this n is 10 to the power 5, right? So that is good enough. Then the only remaining question is how do I calculate the prime factorial faster? There's many faster approach, right? As we show in the gigs in the Stack Overflow. The algorithm I like to use is that you can do Richard Burns modification of that as well. So there is gigs over gigs implementation of this, and those things you need to know ahead of time, right? This prime factorial calculation is a standard thing. You should have it in your library of the code. So that's the approach. It's for me the most interesting thing is you got to study this Benjamin Chi's USACO guide, advanced class, sum over subset. So the homework is obviously to implement of this, right? Combination of 3, let's say, algorithms or approach. One is this worst to best. The second is use a subset, sum over subset for the DPs. The third one is a faster prime factorial calculations. Okay, the homework is to implement this. And we will see you next week. And next week, we will talk about problem number 3. It's again another DP problem with complex logic. Okay, have a good weekend, and we'll talk next time.